And our next speaker is Pavel Lunin, who will discuss modern state-of-the-art data centers and their build-up. Good morning, everyone. I'm Pavel Lunin. I work for Scaleway in France. There is a company, Scaleway. The title is not completely correct. It's about VXLAN, EVPN, fabric. So I will discuss our company. It's a big poster. We're a French company. We have on 100K physical servers, a couple of platform virtual machines. About the networks that I'm going to describe, we have a lot of traffic, about 4 terabits, a lot of hardware, a lot of platforms, old, new, well done, not so well done. And at some point, we decided for the new platforms to create an IP fabric, scalability and all that, to take up less than many years, and to make it modern and nice. So I think that you all know that the architectures of IP fabric is usually applied for such developments, but our colleagues from Google and Facebook and such big companies, their client machines are not our services that we present to the world, so we have to isolate the services so for our customers to live separately with the infrastructural networks, separated IPMI, MI, and the downloading networks to be separated, to be designated. So with the multi-service, we need VRF. And that was one of the business assignments to achieve scalability up to 100,000 virtual machines and so forth. What is IP fabric? If you don't know, this is the topology that was introduced by American mathematicians. I don't remember his name. And this is physical topology with 2 levels. The upper one is spines, and the lower one is leaves, or leaves. This is the aggregation. That's how it looks at every level. There are no links between devices of the same level. They all communicate. Leaves communicate through spines. This is the 3-stage Clos. From one leaf to another, you have to go to the ingoing, the spine, and the outgoing. That's the 3-stage for you. And between 2 uplinks of every leaf, the spines, there's balancing of the load. You can scale it up at spines to have better throughput, more levels with a 5-stage Clos. And you can see the number of leaves that can be introduced for this network. And that is basically endless, limitless. We can use 64 ports, 100 gig by 64. The super spine of 64 ports, that's very big in terms of access ports for the network. So the underlay, to make it work to ping between 2 hosts in this network. This is IP connectivity, simplistic IP connectivity, the underlying topology of Clos. That's what we have in this RFC that was introduced by Microsoft and now Peter Nabok, now working for Facebook. So start with this RFC. There are lots of interesting things there. You should use BGP protocol as the principal one and the only one for routing and for the underlay. This protocol is very good for the internet. The internet is readily scalable, as we know, and BGP protocol is a good one for this purpose. There are some questions about specifics. We can use one autonomous unit for all the leaves, so different for different leaves, BGPC, BFD, or without. You can underlay or not underlay. So this is all described in the RFC I referred to. If you want to make your IP fabric, read it. You have one number of autonomous, so all the leaves have and the spines have the same number. We do not use BFD. The reasons described in the RFC in question, I do not want to delve into any particular detail here, but another point is that here we can believe when it is announced announces something for the spines, it can be the loopback or some links available for other spines, for the other spines. We just do it with the loopback. And we have some difficulties like link visibility, but generally speaking, after some time of operations, we can see that that was the right thing, downline the routes and the scalability and so forth. IPv6 for the underlay. Should we do it? We were afraid of Zhenia's criticism, so to cut a long story short, here's the answer. The hardware in the majority of the cases cannot encapsulate VXLAN for IPv6. So the problem was self-resolving the underlay IPv4 only, but the specificity is that IPv6, so the encapsulated over this with the VXLAN, we experienced no problems. It was all smoothly operational and beautiful. So now the underlay address, many links should be addressed somehow. And the problem of addressing for a multitude of links is usually about the infrastructure, relevant infrastructure, invent IP addresses, EPAM. It's not a secret that it is done in a bad way or chaotically, or something is inventoried, something is not. Tables, matrices, there are two principles of addressing. Number one, like we do it on the internet, have some registrar that says that this address, this block of addresses is designated for such and such customer, such and such client for such and such task. So now we each time take another block and designate it for some purpose and put it in the table. So with the reference, that's how it is done with the internet. The second option is telephone numbering, basically speaking. Some geographic territory gets the code, and for every level of a hotel, so it's 100, 200, and so forth, like numbering of the doors. And we saw those presentations, so let's designate for Russia IP addresses starting with 7 and so forth. In the internet, we cannot use this approach. But when we have the topology that is fixed, the Clos and we do not do VLANs because we want it. We know that the physical topology is like that, and it's going to stay that way. We have to use the approach when topology is encoded in the addresses, like numbering of the hotel rooms. There are advantages and disadvantages for every option. Both options, some addresses have to be cut off because it's not 100 on each floor plate, and the number of links in the fabric can be less than the numbering opportunities, numbering vacancies. So in reality, if we designate blocks in a consecutive way, there is some loss. Inevitably, so to cut a long story short, the topological arrangement, we chose one big block for the fabric, and all the addressing inside is encoded in the topology. If we know that this is a link between such a leaf and such a span, the IDs of leaves and spines encoded inside the system. Quite frankly, the only problem with this approach is that the people, when they see it for the first time in IP world, they are not used to that. That should be done in the consecutive fashion. So, on the one hand, it is not usual. On the other hand, it is intuitive, and we can see intuitively the connection between the leaf and the spine. And human readable aspect is present to a larger degree. No external inventory is needed for the addresses. It's hardly readable, but you can look it up later. There are some examples of leaves getting the odd IDs, and spines always even IDs. So, how we do that? The Underlay IPv4 only without BMD, and we can see similar IS leaf numbers and spine numbers. So it's the same number for leaves and spines and super spines. The 3-level, 5-tier arrangement. The Underlay, it's all pinning perfectly well, but we the multi-service aspect, because we have, in addition to this traffic, we have some auxiliary service sub-network, hypervisors and so forth. It becomes more complicated with this architecture. We have to isolate the services. We have to do different NTs for storages, for the interfaces in the network and the internet. It's a bad idea, sorry. Not such a good idea. So from the point of view of scalability, we say the proportionate number of VRF with custom PCs, and there are VRFs with the proportionate number to hypervisors. So we have to divide by VRF. So the overlay principle has to be applied. We all know it well. VPN have been existing for a score of years, 20 years or something. It's all well known, and data centers, it's a new thing. And if providers have VPLS, that is scalable readily for the data centers, vendors Cisco, Juniper, and others, they are afraid of killing the market of big, expensive routers, and some guys suggested VXLAN for overlay technology for data centers. So when you look on extrapolations, bad IP over BDP, but this is the effect. The standard for overlay For data centers, it's serviceable, and everyone knows it and is used to it. That's backbone VRF. VRFs are designated isolated. Each of them has its own addressing. They can overlap. Nothing new about this. So for the data center, it's a new task. The same thing. So we have a couple of VRFs, one green, one red for internet, for storage, for downloads, and so forth. 3 colors. The same thing, but instead of VXLANs, instead of MPLSs, and that's the only difference, because VXLAN, when it was introduced, there was the control technology. At some point, we were supposed to say that such traffic was supposed to go to the blue or green VXLAN. At the very beginning, with that standard, the mechanism for this whole economy was based on multicast. That was horrible, that was chaotic, and it wasn't a way to go, clearly. At some point, people related to BGPs and so forth came up with the EVPN technology for providers and PLS networks, for the services, VPL, Steroids. That was for the operators. At some point, people thought to themselves, why not using this with VXLAN encapsulation, not NPLS encapsulation. So NPLN was adjusted as a technology. It's flexible, family EVPN BGP for encapsulation of VXLAN type. As a result of that, we have some kind of technology that is, generally speaking, not very much different, but it's basically the same with provider network, PVPN, L2, pseudo wires, VPLS, and so forth. The providers made this for many years. We know about that. We have the literature, we have the people, and basically the same thing. People are doing this for CODs, and we did it for the same purpose. So the first inclusion, the first finding, if you decide to make such fabric, start with MPLS VPN theory. Learn, because many things that should be done in CODs, they are not described in the relevant literature, but they are much better described with the multi-family BGP. All this literature on MPLS should be studied. The right literature is there. MPLS VPN is the destination. VPN is another BGP address family that was invented for NPLS operators, and then they added the opportunity for VXLAN's encapsulation. Originally, VPN was designed for 2 services. That was VPLS, but as some of you might guess, with BGP, MAC addresses, we can signal, we can announce them in BGP. That is something of the sort. It's better than VPLS, but there are some challenges also. And then we decided that technology, VPN as BGP, they started in adding some routes inside, some turn homes, MAC addresses, some for announcement of other things. At some point, people made LP VPN based on EVPN, the 5th type, to announce L3 VPN, like L3 VPN for address family, PLS with detail, and they decided to encapsulate VXLAN, Geneva, GRE, but VXLAN is the standard now, and everyone uses it. and the Geneva is supported, is going to be fashionable, so maybe they will come to terms and be friends. So VXLAN is connection for two VLANs, VXLAN through IP, L2 traffic through IP. Yes, but not just that. VXLAN is not about that. It's about VXLAN is a tunnel of some kind that is not very different from other type of GRA, L2TP. There is some different encapsulation, better or worse, for better or worse, but this is just a tunnel, you can use it for everything, signaling, not signaling. So there you have the toolkit, EVPN address family for propane, and for data play encapsulation. And that is standard. Many vendors support it. Open source products support that a lot. And that's it. So the device to terminate the VXLAN is called VTEP, VXLAN termination point. So another subtle aspect, despite of this being a standard household name, this equipment actually chips and other things, cycles of development, and if you want to do the same thing, you have to be very careful about choosing your hardware, because in order to do what we do, your hardware, your switches, your leaves, the devices to accommodate VXLANs have to do L3 lookup inside VXLAN, the more modern Broadcom Trident 2 Plus. They can do that. Broadcom Trident 2 without Plus cannot do that. So you have to be very careful indeed about that. You have to test it well in advance and ask vendors the right questions. It is not by default, so to speak. So now we made VRF, but on VPNs with the internet, so VXLANs, so we have to come out of the overlays and get down to earth and route this traffic, and we use that edge leaf or border leaf, the standard name. Another leaf that we use here, not the topological, is the same thing. It's the access side connecting with not the fabric, not with the customers, but with the internet, to the backbone for into the internet traffic. This is a special device. We'll see the requirements for scalability, for some other aspects are higher than with the usual top-of-rack switches. These are not the same leaves. They are much more powerful with a greater capacity and specific features. With the underlay, that was all about eBGP, and the overlay is iBGP. All that is based on iBGP address family EVPN, and as with adults, standard backbone, we do that with COD based on protocol, multi-protocol iBGP with a special address family. And as we know, it is scalable with route reflectors, so we cannot connect them without with the iBGP session. So route reflectors, or route reflectors, and what with route reflectors seem standard vanilla, but it is not that easy. We know that it's better to make them off-path and some virtual rig, it should be relatively inexpensive with the processors and so forth. So to cut a long story short, so the spine, so the network equipment, but this is not scalable. If we need another spine, at some point we decide to do something else. Well, we did not want to do it. As a result of that, we had the virtuals, which are also have to available for connection. They should be connected to the server. The server should be connected. It's not that easy, all that. So the service, we have now 40 gig links very often. So it's edge leaf. The only point where we can get BFD, because in order to announce loopback for route reflectors, there's hypervisor and the virtual switch. This virtual platform cannot see the link going up or down, uplink or downlink, and we underlay BFD for each BGP. So if the physical link goes down, we have this convergence that is quick, not slow. Things that we do, and then we have the scalability issues. The number of routes at some point with the EVPN is higher than the capacity of switches allows for. Now, the number of routes is limited with them, so we have this arrangement where we break down our VRF. We shard it with the customer machines, the number of machines. We divide it into small pieces. Sharding is a fashionable word, and we use the classic route target game, and that is described in VPLS literature. Different targets here, and the routes between the leaves are not important directly, and with the edge leaves we have stitching of the VRFs. That's the scheme that we decided upon for the scalability purposes. And here we can see we deploy a new code and create this scheme considering the domain of scalability. Multi-homing with two leaves of the same machine. There's this great technology of PSI. It's standard VPN, but not all the vendors support it. And if you have Juniper only, you can try. If you have, Zen is happy. If it's not Juniper only, that's pain, that's trouble. MCLAC is another approach. Any cast address with the VXLAN to be balanced between the two. You can see the same loop back for the two leaves, the same. With the unicast, there's anycast and balancing of the load. Some part of it comes here, and some part of it comes here, and select here with all this stuff. So this link should not be absorbed in API fabric. It should be transparent full. It should not have any addresses, because everything will be broken in that case. So many of you heard about termination of VXLANs for hypervisors at hosts. We do it for some other tasks. That is not about it. This presentation isn't. We can have some underlay when hypervisors will make VXLANs for special service provision for private networks, but that's a separate project, and all this fabric is not about it. And the last, managerial aspect, how this should be managed. Everything is cool, especially for the people who do backbone. They have this control, designated switch, and another switch for the first and the third for the second. So we cannot afford designated switches for every single power equipment, and it is too expensive, so it's, these sophistications pushing to the network itself. So we use underlays instead for some private domains. They're not presented for internet. And for the switch leaf, we reach out with the underlay, and we think that this approach is quite reasonable, and different vendors manage inside VRF differently, control inside VRF. The control should be at the main routing table, and then we have fewer problems with the control of the switches. And we have some bootstrap because for many racks we have need the provision, the automation for the rack mount cabinets. That's the underlying questions, please. If you have any, if you're not asleep yet. There is a question. Good morning. Good morning, Sergey, Belarus hoster. Tell us, please, you mentioned that you have several data centers. What was the case with the DCI arrangement? Well, to tell you the truth, we haven't experienced this problem yet because our principal service is internet. So we do that locally. It is not, there's no DCI, we do not need it at the backbone. We have our VRFs, and we do that with the edge leaf, we do stitching. That's analogous to inter-VPN option A, when VLANs do their own VRFs on the big bones and for CODs, and we have the multi-LAN between the backbone and edge leaf. And that's, there are sessions at least, just in case, we have the public address loopbacks. And of course, VXLANs are not well protected for support and so forth. But basically, if we decide to do it, we can use public internet for VXLANs between the two leaves to work through the internet. But we do not do it. Thank you.